The universe is a sea of scattered stars and lonely galaxies, or at least, that is what we believed for generations. We pictured cosmic evolution as a slow, steady drift, a gentle expansion scattering matter evenly into the void. But we were wrong. Hidden within the grand tapestry of the cosmos are immense, organized structures so vast they defy logic, patterns woven on a scale that challenges everything we think we know about how the universe works. These are the unexplained clusterings of galaxy superclusters, the universe's greatest architectural mysteries. By the end of this journey, you will see the cosmos not as a random scatter, but as a structured web holding secrets about the very forces that shaped reality. We will confront walls of galaxies so long they should not exist, and voids so empty they seem to erase the laws of physics. What does it mean when the universe itself appears to be organized in ways we cannot yet explain? Our cosmic neighborhood is not as tranquil as it seems. We are caught in a slow, relentless river, a drift of galaxies on a scale so immense it feels like standing still. For decades, astronomers measured this motion and found a puzzle. Our entire galactic group, along with hundreds of thousands of others, is streaming toward a specific, mysterious point in the distant cosmos. This was not a gentle nudge, but a powerful, unexplained pull. The search for the source led them to a discovery in the constellation Centaurus, a discovery that would forever change our understanding of cosmic structure. They called it the Shapley Concentration. This is not a single galaxy or even a cluster. It is a staggering supercluster, an immense gathering of mass so colossal it acts as a gravitational anchor for our entire corner of the universe. Within its bounds lie tens of thousands of galaxies, each one a swirling island of billions of stars like our own Milky Way, all bound together in a single titanic knot of matter. Finding such a dense concentration of galaxies was a profound shock. It directly challenged the long-held belief that on the largest scales, the universe was smooth and uniform, its matter spread evenly like raisins in a rising loaf of bread. The Shapley Concentration was not a raisin. It was an entire cluster of raisins fused together, a lump in the cosmic dough so massive its gravity reaches across hundreds of millions of light years. This immense overdensity became known as the great attractor of its time, a focal point of gravitational influence so strong it dominates the motion of everything around it. Our local group of galaxies, which includes Andromeda and the Milky Way, is caught in this flow. We are not moving randomly. We are being pulled, along with an immense sheet of other galaxies, toward this distant concentration of mass. This motion is so significant, it even leaves an imprint on the oldest light in the universe, the cosmic microwave background. As we move toward the Shapley Concentration, the light from ahead appears very slightly warmer, and the light from behind appears very slightly cooler. This temperature difference, called the dipole, is a direct signature of our journey, a cosmic speedometer reading that points back to the immense gravitational tug of this distant structure. So we are not floating in a calm sea. We are in a current, drawn by a hidden giant whose full nature we are still striving to understand. Yet even the immense pull of the Shapley Concentration was only part of a much larger story. As astronomers mapped the cosmos with greater precision, they began to see a pattern, a cosmic architecture emerging from the data. Then, in 2005, a discovery was made that redefined the very meaning of the word large. Buried within the Sloan Digital Sky Survey, a monumental project to map 1/4 of the sky, scientists found a structure so immense it seemed to break the rules. They named it the Sloan Great Wall. This was not a mere cluster or a dense concentration. It was a filament, a colossal thread of galaxies stretching across an almost unimaginable distance. Picture a wall of galaxies over 1.37 billion light-years long. To grasp that scale, consider that a single light-year is the distance light travels in 1 year, moving at about 671 million miles per hour. Now multiply that journey by 1.37 billion. It is a length so vast that light leaving one end of the structure when the first complex life began forming on Earth would only now be reaching the other end. The Sloan Great Wall is not a solid barrier, of course. It is a vast, interconnected web of galaxy groups and clusters, a dense highway of matter woven through the cosmic void. Its discovery shattered all previous records for the largest known structure, and in doing so, it posed a profound and unsettling question to cosmologists. Our best models of the universe are built on a principle called the cosmological principle, which states that on the largest scales, the universe should look roughly the same in every direction and from every point. Matter should be evenly distributed, like a finely mixed batter. Finding a lump the size of the Sloan Great Wall is like finding a single chocolate chip in your batter that is larger than the mixing bowl itself. The statistical probability of such an immense structure forming through the random, gentle processes described by our standard model of cosmology is incredibly low. It is an outlier so extreme it forces us to wonder if our understanding of those early formative processes is incomplete. Did some unknown force in the infant universe stitch these galaxies together on this impossible scale, or are we simply seeing a statistical fluke, a cosmic roll of the dice that just happened to produce a structure of such breathtaking size? The wall stands as a silent challenge, a line drawn across the heavens asking us to explain how it came to be. But even the staggering scale of the Sloan Great Wall was not the final word. A deeper mystery was waiting, one that would push our understanding of cosmic structure to its absolute breaking point. In 2013, astronomers studying a different kind of cosmic signal stumbled upon evidence of something that should not exist. They were not looking at galaxies directly. Instead, they were tracing the cataclysmic deaths of massive stars, events so violent they release more energy in a few seconds than our Sun will in its entire 10 billion-year lifetime. These are gamma-ray bursts, the most powerful explosions in the universe since the Big Bang itself. By mapping the locations of these brilliant, fleeting flashes, scientists could use them as beacons, as tracers for the underlying mass in the distant cosmos. Where there is more mass, there are more stars, and therefore more of these stellar explosions. What they found was a pattern, an apparent clustering of gamma-ray bursts in the directions of the constellations Hercules and Corona Borealis that suggested an immense, dense structure. The data pointed to a wall of galaxies of such incomprehensible size that it dwarfed everything else we had ever seen. They called it the Hercules Corona Borealis Great Wall. Its proposed scale is almost beyond human comprehension. Early analyses suggested it could span an incredible 10 billion light-years. To put that in perspective, the entire observable universe is only about 93 billion light-years across. This single structure, if real, would account for over 10% of the observable diameter of everything that exists. It would be a filament of galaxies and galaxy clusters so vast it would make the Sloan Great Wall look like a local neighborhood. This claim ignited immediate and intense debate within the astrophysics community. The controversy centers on methodology and statistics. using gamma-ray bursts as mass tracers is a brilliant but indirect technique. It is like trying to map a city at night by only plotting the locations of lightning strikes. You get points of light, but inferring the full street grid and skyline from those sparse points is incredibly challenging. Critics argued that the apparent clustering could be a statistical fluke, a chance alignment of these rare explosions that does not reflect a true, connected physical structure. The sheer proposed size of the wall is the core of the problem. A structure 10 billion light-years long would not just challenge the cosmological principle, it would shatter it. The principle relies on the idea that the universe is homogeneous and isotropic on the largest scales, meaning it should have no preferred directions or giant, defining features. A wall of that magnitude would be a preferred direction. It would be a feature so dominant that the universe, from our vantage point, would look fundamentally different in one direction compared to all others. It would suggest that either our standard model of cosmic evolution is missing a crucial ingredient, or that we are seeing a remnant of the universe's earliest moments, a fossil imprint from a time before inflation smoothed everything out. The debate remains unresolved. Is the Hercules Corona Borealis Great Wall the ultimate cosmic structure, a real architectural marvel that rewrites the textbooks, or is it a magnificent mirage, a trick of sparse data and human pattern seeking? For now, it stands as the frontier of this mystery, a ghost in the gamma-ray data that dares us to look deeper and question our most fundamental assumptions about the cosmos. Long before we mapped the Sloan Great Wall or debated the Hercules Corona Borealis, there was a first crack in the cosmic facade. In the 1980s, a team at the Harvard-Smithsonian Center for Astrophysics was conducting a massive survey, meticulously cataloging the redshifts of galaxies. Redshift is the key. When an object moves away from us, the light it emits stretches, shifting toward the red end of the spectrum. By measuring this shift, astronomers can determine not just how fast a galaxy is receding, but also its distance. The team was painting a three-dimensional map of our local universe, and what they found was utterly unexpected. Instead of galaxies scattered evenly like stars on a clear night, their map revealed a startling pattern. A vast, dense concentration of galaxies formed a colossal, sheet-like structure stretching across the sky. They had discovered the first Great Wall. This structure, now known as the CF2 Great Wall, or often the Coma Wall, was a revelation. It bridged two famous and massive galaxy clusters, the Coma Cluster and the Leo Cluster, like a dense cosmic highway connecting two major cities. The scale was staggering for its time, spanning over 500 million light-years in length. For perspective, that is a distance so vast, it would take a beam of light, the fastest thing in the universe, 500 million years to travel from one end to the other. The discovery fundamentally shattered the prevailing view of cosmic structure. Before this map, the dominant model was often described as Swiss cheese. Galaxies and clusters were thought to be like holes in the cheese, embedded in vast, empty voids. The universe was seen as mostly nothing, with islands of matter floating in the great dark. The CF2 Great Wall changed that picture forever. It showed that galaxies were not isolated islands, they were connected. This immense wall was evidence of a vast, interconnected architecture, a filament in a grand cosmic web. That term, the cosmic web, entered our vocabulary because of this discovery. It describes the universe's large-scale structure as a network of dense filaments, where galaxies cluster like beads on a string, intersecting at massive nodes where great clusters reside. Between these filaments lie the immense, empty cosmic voids, regions of space that can be hundreds of millions of light years across, containing almost no galaxies at all. The Coma Wall was our first clear glimpse of this web. It proved the universe was lumpy on the grandest scales, that matter clumped together in ways our theories had not fully predicted. This single structure moved us from a simple model of isolated clusters to a dynamic, connected tapestry, setting the stage for every giant wall discovery that would follow and forcing cosmology to confront a universe far more structured and far more mysterious than we had ever dreamed. Our own galaxy is not a solitary wanderer in an empty sea. We are part of the architecture, embedded within one of these immense walls. The grand structure we call home is known as the Pisces-Cetus supercluster complex. It is not a single supercluster, but a sprawling network of them, a vast filament or sheet of galaxies that forms one of the major threads in the local cosmic web. This complex is our neighborhood on a scale so grand it is almost impossible to visualize. It contains dozens of known galaxy clusters and groups, including our own local group with the Milky Way and Andromeda, the Virgo cluster, and the Fornax cluster, all woven together by gravity into a single, coherent sheet of matter. For a long time, we did not know we were inside something so immense. Mapping the cosmos from within is like trying to map a forest while standing among the trees. You can see the trunks around you, but the full pattern of the woodland remains hidden. It was only through decades of painstaking redshift surveys, measuring the distances to thousands of nearby galaxies, that the outline of our home wall began to emerge. Astronomers slowly plotted the three-dimensional positions of these galaxies and saw a pattern. They were not scattered randomly. Instead, they were arranged in a vast, flattened structure, a cosmic continent with our local group situated on its outskirts. This realization was profoundly humbling. We are not in an isolated suburb of the universe. We reside within a sprawling metropolis of galaxies, a sheet that stretches for hundreds of millions of light years. The Pisces-Cetus complex challenges the comforting idea of cosmic isolation. It demonstrates that even our quiet corner of space is part of a much larger, organized system. This immense local wall is itself moving, caught in the gravitational currents flowing toward the even greater mass of the Shapley Concentration. So we are participants in this grand cosmic motion, residents of a vast structure we are only beginning to fully map. Knowing we live inside one of these walls answers some questions, but raises even deeper ones. If our local universe is this structured, what does it imply about the true scale of the cosmic web in its entirety? The cosmic web is a tapestry of light and shadow, of immense walls and the profound emptiness between them. If the great walls are the threads of this tapestry, then the voids are the dark spaces that give the pattern its shape. And among these voids, one stands out as a realm of almost perfect nothingness. This is the Boots void, a spherical region of space so empty it has been called the Great Nothing. Its scale is staggering, roughly 330 million light-years in diameter. To cross it, a beam of light would need to travel for over 300 million years without encountering almost anything of note. Within this colossal volume, astronomers have found only a handful of galaxies, in a region of space that, according to average cosmic density, should contain thousands of bright galaxies. There are perhaps 60. It is a staggering underdensity, a hole in the cosmic web so vast it feels like an erasure of the universe itself. The existence of the Boots void is as challenging to our models as the giant walls. Our understanding of cosmic structure formation relies on gravity pulling matter together over billions of years. dense regions grow denser, forming clusters and filaments. The less dense regions between them get left behind, emptying out as matter drains toward the gravitational wells. This process naturally creates voids. But the Boots void is not just a void, it is a supervoid of an extreme size. Its scale pushes the limits of what this gentle, gravity-driven process should reasonably produce. It is too big and too empty. One leading theory suggests it may not be a single, primordial emptiness, but the result of a cosmic merger. Imagine several smaller voids, like soap bubbles in a sink, slowly drifting together over cosmic time. Their walls touch, then merge, and eventually they coalesce into one gigantic, spherical region of emptiness. This process could explain its near-perfect spherical shape and its extreme underdensity. Another, more speculative idea is that its formation was influenced by something in the very early universe, a rare, large-scale fluctuation in density that left this particular patch of space with far less raw material to begin with. Whatever its origin, the void is not completely empty. The few galaxies that do exist within it are isolated island universes, separated by distances so great that from one, the others would be barely visible specks in a forever dark sky. Their very presence is a clue, suggesting that even in the greatest nothing, the seeds of something persisted. The Boots void and the Great Walls are two sides of the same cosmic coin. They represent the extreme peaks and valleys in the distribution of matter. Finding such a vast emptiness is statistically as surprising as finding a wall of galaxies 10 billion light-years long. Both extremes test the standard model of cosmology, which predicts a certain range of structure sizes. These colossal features seem to sit at the very edge, or even beyond, that predicted range. They ask us a fundamental question. Is our universe merely a statistical outlier, a rare roll of the dice that produced a few structures of breathtaking scale? Or are these giants and voids telling us that our theories of how gravity sculpted the cosmos from the smooth aftermath of the Big Bang are missing a crucial piece? The void's profound silence is, in its own way, as loud as the brilliant flash of a gamma-ray burst. It is a blank space on the map that demands an explanation, a haunting reminder that to understand the universe's greatest structures, we must also understand its greatest absences. This cosmic architecture does not just shape the distant universe, it defines our immediate surroundings with startling clarity. For decades, astronomers have been meticulously measuring the distances to our closest galactic neighbors, building a precise, three-dimensional map of our local cosmic neighborhood. What they found was not a gentle, even distribution of galaxies around us. Instead, the data painted a picture of a profound and unsettling emptiness pressing right up against our doorstep. We are not floating in a dense sea of stars. We are perched on the precipice of a vast, dark chasm known as the local void. This region of space, beginning just beyond our own local group of galaxies, is a sprawling underdensity, an emptiness that stretches for at least 150 million light-years in one direction. It is a place where galaxies are remarkably scarce, a true desert on a cosmic scale. The discovery came from measuring the precise motions of galaxies very close to us. Astronomers noticed something peculiar. While the grand pull of the Shapley Concentration was drawing us in one direction, our local group and several nearby galaxies showed an additional, unexpected motion. We were not just being pulled, we were also being pushed. The source of this push was not an immense concentration of mass, but rather a profound lack of it. Gravity works in two ways. It attracts matter toward dense regions, but it also, in effect, pushes matter away from empty ones. Think of it like being in a crowded room that suddenly has one empty corner. The pressure of the crowd around you would naturally make you drift toward that empty space. In the cosmos, the dense walls of the cosmic web exert a gravitational pull, while the vast voids create a kind of negative pressure, a repulsive effect. The local void is our local empty corner. Because it contains so little mass, its gravitational influence is weak. The denser regions on the other side of us, like the Virgo cluster and the broader Pisces-Cetus supercluster complex, have a stronger pull. This imbalance effectively shoves us away from the void and toward the denser structures. This means the motion of our Milky Way galaxy is a complex dance, a result of multiple gravitational influences. The mighty tug of the Shapley Concentration sets our long-term direction across hundreds of millions of light years, but superimposed on that grand current is this local repulsion from the void at our backs, a subtle but significant nudge that adjusts our path. We are not merely passengers on a river flowing toward a distant attractor. We are also being gently expelled from a silent, expanding desert. This realization reframes our place in the cosmos. We do not inhabit a typical region of space. We live on a frontier, on the borderlands between a dense filament of the cosmic web and one of its great empty chambers. The local void is a constant, unseen presence, its emptiness actively shaping our galaxy's journey through the universe. It is a reminder that the forces sculpting the cosmos are not just about where the matter is, but also about where it is not. The nothingness itself has a gravitational voice, and it is speaking to us in the subtle drift of the stars. But the local void is merely a shadow compared to a far more controversial emptiness proposed to surround us. Recent observations have begun to hint at a staggering possibility that our entire local cosmos, out to a distance of several billion light years, exists inside a vast bubble of lower density. This theoretical structure is called the KBC void, named for the researchers Keenan, Barger, and Cowie, who first brought its evidence into sharp focus. Their work did not rely on mapping individual galaxies alone, but on measuring the average density of matter across immense volumes of space. They counted galaxies, measured the X-ray glow of hot gas in clusters, and studied the distribution of all forms of luminous matter. The results consistently pointed in one direction. Within a sphere roughly 2 billion light-years in radius centered on us, the density of matter appears to be significantly lower than the established cosmic average. We are not just on the edge of a void, we may be floating near the center of the largest underdensity ever proposed. The implications of this are profound, and they reach directly into one of cosmology's most heated modern debates, the Hubble tension. The Hubble constant is a critical number. It describes how fast the universe is expanding at the present time. We have two primary ways to measure it. One method looks at the local universe, using relatively nearby stars and supernovas as cosmic mile markers to gauge expansion speeds. The other method looks back to the very early universe, using the imprint of the cosmic microwave background, the afterglow of the Big Bang, to predict what the expansion rate should be today. These two methods, both meticulously checked and rechecked, disagree. They yield different numbers for the Hubble constant. This discrepancy is the Hubble tension, and it suggests a potential crisis in our standard model of cosmology. This is where the KBC void enters the story. If we truly reside in a giant underdensity, a cosmic bubble, it could act like a lens distorting our local measurements. Imagine you are trying to measure the slope of a hill, but you are standing in a deep, wide pit on that hillside. Your local perspective would be skewed. making the overall hill seem steeper or shallower than it truly is. In cosmic terms, living inside a low-density bubble would affect how we perceive the expansion rate in our immediate vicinity. Gravity from surrounding denser regions outside the bubble could subtly alter the motions of nearby galaxies and the apparent brightness of supernovas, which we use as standard candles to measure distance. This local distortion could mean our measurement of the present-day expansion rate is slightly off, potentially bringing it into alignment with the prediction from the early universe. In essence, the KBC void could be the missing piece that resolves the Hubble tension, not by changing the laws of physics, but by correcting for a colossal sampling error in our cosmic neighborhood. Of course, the idea remains highly contentious. Many cosmologists argue that such a vast underdensity is statistically extremely unlikely in our standard model, almost as unlikely as the giant walls we have discussed. It would be another colossal outlier, yet the evidence from galaxy counts persists, whispering that our place in the cosmos might be even more unusual than we thought. Are we cosmic outliers living in a grand bubble? And if so, does that bubble hold the key to reconciling our deepest measurements of the universe's expansion? The silence of this possible void speaks directly to the loudest debate in modern cosmology. Our cosmic address just got a dramatic rewrite. For generations, we thought our home was the Virgo supercluster, a vast collection of galaxy groups anchored by the mighty Virgo cluster. But that map was incomplete, a local view that missed the true grandeur of the structure we are part of. In 2014, a team of astronomers led by Brent Tully unveiled a new way of seeing the cosmos, and with it, they gave us a new home. They named it Laniakea, a Hawaiian word meaning immense heaven. This is not just another cluster or group. Laniakea is a supercluster of staggering scale, a continent of galaxies 100,000 times more massive than our own Milky Way, spanning over 500 million light-years. It contains approximately 100,000 large galaxies and perhaps a million smaller ones, all woven together by the relentless pull of gravity into a single, flowing system. The key to this discovery was a shift in perspective. Instead of just mapping where galaxies are, the team meticulously charted how they are moving. Every galaxy has two motions. One is the general expansion of the universe, carrying it outward like a leaf on a receding tide. The other is a peculiar velocity, a local drift caused by the gravitational tug of nearby matter. By subtracting the uniform expansion, astronomers could map these peculiar flows, tracing the subtle rivers of motion in the cosmic landscape. What they saw was breathtaking. Across our entire region of space, galaxies are not moving randomly. They are streaming along coherent pathways, like water droplets in a vast watershed, all flowing toward a common gravitational center. This technique revealed the true boundaries of Laniakea. Its edge is not defined by a density of stars, but by a watershed divide in space itself. Imagine a vast mountain range in the cosmos. On one side, all galactic rivers flow into the Laniakea basin. On the other side, they flow away toward a different gravitational destiny. Within our home supercluster, every stream, every filament of galaxies converges. They flow along immense cosmic highways, down gravitational slopes, toward a single focal point hidden behind the dust of our own Milky Way's central bulge. This focal point is the Great Attractor, a mysterious region of immense mass that has been pulling on us for billions of years. Laniakea, then, is the entire drainage basin for this Great Attractor. It redefines familiar landmarks. Our former home, the Virgo supercluster, is not a separate entity. It is merely a dense knot within one of Laniakia's primary filaments, like a major city along a great river. The Milky Way sits in a quieter suburban spur of this filament, slowly making its way along with the flow. We are part of a celestial river system of unimaginable size, all of us from the Great Virgo cluster to our own modest galactic neighborhood, caught in a slow, inevitable journey toward a hidden gravitational heart. This new map does more than give us a grander address. It shows us that the universe is organized by motion as much as by matter. We are not just located in a place, we are participants in a flow, residents of a dynamic continent whose shape is written in the steady drift of 100,000 galaxies. While Laniakia defines our local flow, the grandest rivers of galactic motion extend far beyond our superclusters' borders. To understand them, we must journey to the deep southern skies, to a region of staggering density that rivals even the great Shapley Concentration. Here, in the constellations of Horologium and Reticulum, lies a gravitational titan, one of the most massive superclusters ever mapped. The Horologium Reticulum supercluster is a sprawling metropolis of galaxies, a dense knot in the cosmic web so immense it exerts a commanding influence over an entire sector of the universe. Its core is not a single entity, but a rich collection of massive galaxy clusters, each one a swirling hive of thousands of galaxies bound together by gravity. These clusters are themselves connected by thick filaments of galaxies, forming a dense, interconnected network that spans hundreds of millions of light years. The total mass contained within this supercluster is almost beyond calculation, a gravitational anchor point of profound significance. This supercluster's location is no cosmic accident. It resides in the same general direction as the Shapley Concentration, the great attractor we are all streaming toward. In fact, Horologium Reticulum is considered a major outlying component of that even larger mass concentration. Think of the Shapley region as a great mountain range and Horologium Reticulum as one of its tallest, most formidable peaks. Its sheer mass makes it a dominant node in the cosmic web, a junction where multiple galactic filaments converge and intertwine. This gravitational powerhouse does not simply sit still, it actively shapes the motion of everything around it. The bulk flow, that immense river of galaxies including our own Laniakea supercluster, is not driven by Shapley alone. It is a combined pull, a symphony of gravitational attraction from all the major mass concentrations in that direction, with Horologium Reticulum playing a first-chair role. Its immense gravity contributes significantly to the current that carries us across the cosmos. This reveals a crucial truth about the universe's large-scale structure. The cosmic web is not a static spider's silk frozen in space. It is a dynamic, flowing system, with galaxies and even whole superclusters moving along its filaments toward the densest nodes. Horologium Reticulum is one of those ultimate destinations, a gravitational well so deep it draws matter from vast distances. Its existence helps explain why the bulk flow persists over such incredible scales. The combined pull of multiple giants like this one creates a slope in spacetime so gentle and vast we can barely perceive it, yet so powerful it guides the motion of hundreds of thousands of galaxies. Studying this distant supercluster is like studying the source of a great river. It helps us understand the forces that set the entire system in motion. What other colossal nodes, hidden behind the veil of the Milky Way's dust, are still waiting to be found, and how might they reshape our map of the universal currents we are riding? Far to the north of the celestial equator, nestled within the constellation of the Northern Crown, lies a dense and ancient gathering of mass. The Corona Borealis supercluster is not the largest structure we have found, but it may be one of the most perfectly formed. Unlike the sprawling, filamentary walls that stretch across billions of light years, this supercluster presents a remarkably compact, almost spherical shape. It is a dense knot in the cosmic web, a textbook example of what astronomers call a rich supercluster, containing a stunning concentration of galaxy clusters and groups all bound together by their mutual gravity. Within its bounds, the density of galaxies is exceptionally high, creating a region of space that feels crowded, even by cosmic standards. This makes it a pristine laboratory for studying the violent processes that shape the universe's largest structures. At the heart of this supercluster, astronomers observe not a state of calm, but one of controlled chaos. The immense gravitational pull of so much mass packed into a relatively small volume sets the stage for a relentless cosmic dance. Individual galaxy clusters, each home to thousands of galaxies, are not stationary. They orbit one another, drawn closer over eons by the unyielding tug of gravity. This leads to the most energetic events in the universe since the Big Bang cluster mergers. When two such massive clusters collide, it is a slow-motion catastrophe of unbelievable scale. The galaxies themselves, vast as they are mostly empty space, so they pass by one another like ghosts, rarely touching. But the superheated gas that fills the space between the galaxies, known as the intracluster medium, is another story. This thin, multimillion-degree plasma is squeezed and shocked by the collision, creating immense shockwaves that ripple through the supercluster and emit powerful X-rays that we can detect across the universe. Studying the Corona Borealis supercluster allows us to witness these mergers in various stages, from clusters just beginning their long gravitational courtship to those in the final, violent throes of coalescence. Each merger is a cosmic experiment, revealing how superclusters grow and evolve over time. The energy released in these collisions is staggering, capable of accelerating particles to near light speed and shaping the magnetic fields that thread through the void. By analyzing this dense, spherical supercluster, we gain crucial insights into the life cycle of all large-scale structure. It shows us that the cosmic web is not a frozen architecture, but a dynamic, ever-changing construction site, where gravity is the master builder, and cluster mergers are the colossal tools it uses to assemble the universe. What we learn from this distant, crowded realm helps explain the history of our own local supercluster, Laniakea, and the fate that likely awaits all such gatherings of galaxies in the far, far future. Just beyond our local void, the cosmic web weaves a thread of astonishing clarity. This is the sculptor wall, a grand filament of galaxies that forms a major backbone of our home supercluster complex. Stretching across the southern skies, it is one of the closest and most prominent examples of a great wall to our own galactic neighborhood, a mere 100 million light-years away. In cosmic terms, that is right next door. Its proximity is a gift to astronomers, offering an unprecedented close-up view of how galaxies live and evolve within the dense environment of a cosmic filament. The sculptor wall is not an isolated structure. It is a vital connective thread within the sprawling Pisces-Cetus supercluster complex, linking together several rich clusters and groups of galaxies. You can think of it as a great celestial highway, with dense galactic cities at its interchanges and quieter rural stretches in between. This wall provides a direct physical connection, showing us how the various nodes of our local cosmic web are literally tied together by these rivers of stars. Because it is so close, we can study it in exquisite detail. Telescopes can resolve individual stars within its galaxies, measure their chemical compositions, and chart the rates at which new stars are being born. This turns the sculptor wall into a giant natural laboratory. Scientists can ask profound questions about how a galaxy's environment shapes its destiny. Does living in a dense wall, surrounded by neighbors and bathed in different gravitational tides, change how a galaxy grows? The evidence suggests it absolutely does. Observations reveal a clear pattern. The galaxies nestled deep within the densest knots of the wall, where clusters meet, are often old, red, and elliptical. Their star-forming days are largely over, their gas used up or stripped away by violent interactions with their crowded surroundings. They are cosmic retirees. But as you move out along the filament, away from the crowded urban centers and into the quieter suburban stretches, the galaxy population shifts. Here, spiral galaxies become more common, their beautiful disks still rich with the cold gas needed to birth new generations of stars. The sculptor wall shows us a gradient of galactic life, a direct link between a galaxy's place in the cosmic web and its current state of evolution. This environmental effect is a crucial clue. It tells us that a galaxy is not an island. Its fate is not determined solely by the conditions of its birth, but is continuously influenced by the neighborhood it finds itself in over billions of years. The gentle tidal forces from the wall's overall mass, the occasional close encounter with a neighbor, and the density of the intergalactic gas all leave their mark. By studying this nearby wall, we get a template for understanding how all such filaments, including the distant and colossal ones we cannot see as clearly, influence the story of the universe's structure. The sculptor wall is a masterclass in cosmic ecology, demonstrating that to understand a single galaxy, you must first map the immense continent it calls home. The cosmic web is not built of walls alone. Between its great sheets and dense clusters flow more subtle structures, the delicate threads that stitch the entire tapestry together. One such thread lies in our southern sky, a faint but coherent stream of galaxies known as the Fornax-Eridanus cloud. This is not a dense, towering wall. Instead, it is an elongated, low-density bridge of galaxies stretching across the void, connecting two significant clusters, the Fornax cluster and the Eridanus cluster, like a faint, celestial river linking two lakes. Its galaxies are not packed tightly together. They are sprinkled along a vast corridor, a gossamer filament of light against the dark. This cloud represents something fundamental, the very scaffolding of the universe. It is along these faint, filamentary pathways that galaxies are thought to travel over billions of years, slowly draining from the quieter suburbs of the cosmos into the dense, urban centers of the great clusters. The Fornax-Eridanus cloud is a snapshot of this process in action, a highway system in its early stages. Within its loose embrace, galaxies move under the gentle but relentless pull of gravity, not toward a single point, but along the filament itself, funneling toward the denser nodes at either end. This illustrates a core principle of cosmic evolution called hierarchical growth. The universe did not build its great cities all at once. It started with tiny seeds of density in the early cosmos, which grew by pulling in matter from their surroundings. First, individual galaxies formed. Then, gravity drew these galaxies together into groups. Groups then merged or were pulled along filaments into clusters. And clusters themselves, like Fornax and Eridanus, are drawn together over even longer timescales, often along supercluster filaments, to build the immense structures we see today. The Fornax-Eridanus cloud is a middle chapter in this story. It shows us the infrastructure, the cosmic pipelines through which the raw material of galaxies flows to feed the growth of larger structures. Studying such a nearby and clear filament allows astronomers to test their models of how gravity sculpts the universe over time. They can measure the velocities of galaxies within the cloud to see if they are indeed streaming along its length, and map the distribution of the faint intergalactic gas that is thought to permeate these filaments, the fuel for future generations of stars. In its subtle, sprawling form, this cloud holds a quiet truth. The largest structures in existence are built one galaxy at a time, along roads of gravity so faint we are only just learning to see them. A sweeping arc of light traces a path across the northern sky. This is the Perseus-Pisces supercluster, one of the most dominant and graceful filaments in our entire cosmic neighborhood. Unlike the spherical density of Corona Borealis or the sprawling continent of Laniakea, this structure presents itself as a long, elegant chain, a string of galaxy clusters and groups that stretches for hundreds of millions of light years. From our vantage point on Earth, it forms a magnificent, curving wall against the darkness, a backbone of the local universe. Its placement is no accident, for this Great Wall serves as a defining border. It forms one entire side of the immense local void we discussed earlier. Picture a canyon of almost perfect nothingness, and on one of its sheer cliffs, a glittering metropolis of galaxies. The Perseus-Pisces supercluster is that glittering cliff face, its dense concentration of matter standing in stark relief against the profound emptiness pressing against it. This dramatic contrast is not just a visual spectacle, it is a physical relationship. The gravitational pull of this immense wall of galaxies is one of the primary forces helping to empty out the void beside it, drawing matter away and deepening the cosmic abyss. But the influence of this supercluster may run even deeper than gravity alone. Recent and astonishing observations suggest that the largest structures in the universe might not just gather galaxies, they might also twist them. Astronomers studying the Perseus-Pisces filament have noticed something peculiar about the galaxies within it. They do not appear to be oriented randomly. Instead, there seems to be a tendency for these galaxies, particularly the spiral ones, to align their axes of rotation with the direction of the filament itself. It is as if the galaxies are lining up, like compass needles pointing along the invisible highway of the cosmic web. This is a profoundly strange idea. A single galaxy is an island universe of hundreds of billions of stars, spinning under its own immense gravity. What possible force could reach across millions of light years to influence which way it turns? The answer may lie in the very origins of cosmic structure. The leading theory suggests that these alignments are fossil relics, imprints from the universe's infancy. In the first moments after the Big Bang, tiny quantum fluctuations were stretched to enormous sizes by a period of hyper-expansion called inflation. These fluctuations became the seeds for all future structure. Crucially, these seeds were not perfectly round. They had slight directional preferences, like stretched taffy. As gravity amplified these seeds over billions of years, pulling matter into filaments and walls, it also imparted a subtle spin to the gas clouds that would eventually collapse into galaxies. That primordial spin axis could be preserved, locked in alignment with the larger filament that birthed it. If confirmed, this means that when we look at the graceful tilt of a spiral galaxy in the Perseus-Pisces chain, we might be seeing the ghost of a quantum ripple from the dawn of time, magnified to a scale beyond human imagination. The supercluster is not just a collection of galaxies, it is a cosmic conductor, orchestrating the orientation of its stellar inhabitants through a memory written in gravity. Deep in the northern sky, far beyond our local web of walls and voids, lies a ghostly thread from a younger universe. The Lynx Ursa Major filament is a colossal structure, a chain of galaxy clusters and groups stretching across 1 billion light-years, but its true significance lies not in its size, but in its distance. We see it not as it is today, but as it was when the universe was only about half its current age, a staggering 7 to 8 billion years in the past. This makes it a time capsule, a fossilized snapshot of cosmic architecture from an era when the universe was far more bustling and energetic. By studying this distant filament, astronomers are not just mapping a structure, they are conducting an archaeological dig into the adolescence of the cosmic web. Back then, the universe was denser, and the process of structure formation was running at a fever pitch. Galaxies were colliding and merging more frequently, and vast reservoirs of cold gas were fueling furious bursts of star formation. The Lynx Ursa Major filament lets us see how superclusters and their connecting threads were being assembled during this dynamic period. We can compare its properties to the mature, settled structures we see in our local, present-day universe, like the Perseus-Pisces supercluster or our home in Laniakea. The differences are telling. The distant filament appears less consolidated, its galaxies more actively forming stars, and its overall shape perhaps more ragged and less defined than the clean, sharp walls we see nearby. This is exactly what our models of cosmic evolution predict. The gentle pull of gravity acting over billions of years gradually draws galaxies out of the faint clouds and into the dense, sharp-edged filaments and clusters we recognize today. The Lynx Ursa Major structure is a crucial piece of evidence in this grand timeline. It shows us the cosmic web in a state of active construction. By measuring the motions of galaxies within it and charting their distribution, astronomers can test how well our simulations of gravity and dark matter recreate this intermediate stage of growth. Does the filament have the same density profile as our models suggest? Are the galaxy clusters within it already showing signs of merging, or are they still separate islands beginning to feel each other's pull? Each answer helps refine our understanding of the universal forces that have spent 10 billion years weaving galaxies into the grand tapestry we now observe. This distant thread of light is a bridge across time, connecting the vibrant, chaotic universe of the past with the majestic, ordered structures of the present, showing us that the Great Walls were not born fully formed, but were patiently built, one galaxy at a time, over the lifetime of the cosmos. The southern skies hold a second, silent giant. Not far from the galactic plane, in the constellation of Microscopium, astronomers have mapped another profound emptiness, a spherical region of space that rivals the Bootes void in its scale and mystery. The Microscopium void stretches for hundreds of millions of light-years, a bubble of near-nothingness that contains only a sparse sprinkling of lonely galaxies. Its discovery confirmed something crucial, that the Bootes void was not a one-of-a-kind fluke. These immense cosmic deserts are a fundamental feature of the universe's architecture, part of a vast and structured hierarchy. Voids come in all sizes, from small, bubble-like pockets only a few tens of millions of light-years across, to the titanic supervoids like Bootes and Microscopium that push the very limits of what seems possible. This hierarchy is not random, it is a direct prediction of our cosmological models. the standard model of cosmology, with its dark energy and cold dark matter, simulates the evolution of the universe from a nearly smooth beginning. In those simulations, gravity amplifies tiny initial ripples, pulling matter into the filaments and nodes of the cosmic web, and in doing so, it naturally leaves behind empty regions. The sizes and shapes of these voids in the simulations should match what we see in the real sky, and for the most part, they do. The distribution of small and medium voids fits the predictions beautifully. But the giants, the supervoids like Boots and Microscopium, present a subtle challenge. They appear just a little too large and a little too perfectly spherical to be easily explained by the gentle, gravity-driven process alone. A perfectly spherical void is a clue. In the chaotic gravitational tug-of-war of cosmic evolution, you would expect voids to be irregular, misshapen things, like bubbles in a sink that have merged and warped. A near-perfect sphere suggests something else, perhaps that the void formed from a single, exceptionally large underdensity in the primordial universe, a rare smooth patch that never had much matter to begin with. Or it could imply that our understanding of the forces at play, including the push of dark energy, needs refinement. The properties of these largest voids have become a critical testing ground. By counting them, measuring their shapes, and mapping their distribution, cosmologists are conducting a cosmic audit. Do we see the number of supervoids that our models predict? Are they arranged in the patterns we expect? Each new map of the distant universe adds data to this test. The continued existence of these immense, spherical silences whispers that while our picture of cosmic evolution is broadly correct, the finest details of how nothingness itself is sculpted may still hold surprises. The pull we feel is not from a single, monstrous beast, but from a crowded city hidden behind a curtain. The Great Attractor, that legendary name for the force dragging our supercluster, is actually a vast and diffuse concentration of mass in the constellation Centaurus. It is the combined gravitational pull of several rich galaxy clusters and the dense filament of the cosmic web that connects them, a sprawling metropolitan area of the universe rather than a lone skyscraper. For decades, its true nature remained one of astronomy's most frustrating mysteries, not because it was too distant, but because it lay directly behind the heart of our own galaxy. This region is called the Zone of Avoidance, a thick band of gas, dust, and stars from the Milky Way's disk that completely obscures our optical view of the cosmos beyond. It is like trying to see a distant city through a dense, permanent fog bank. The visible light from the galaxies that make up the Great Attractor is absorbed and scattered by this intervening murk, leaving a blank spot on our maps right at the center of the gravitational puzzle. To finally see what is pulling us, astronomers had to change the light they were looking for. They turned to wavelengths that can pierce the galactic veil, primarily infrared and radio. Infrared light, with its longer wavelengths, is less easily scattered by fine dust grains. Space telescopes like the Wide Field Infrared Survey Explorer have stared into the zone, revealing thousands of previously hidden galaxies glowing with the heat of their stars. Radio telescopes listen for the faint whisper of hydrogen gas, the primary fuel of galaxies, which emits a characteristic signal unaffected by dust. These combined efforts are like giving the cosmos a new set of eyes. Slowly, painstakingly, a map of the hidden realm is emerging. We now see that the core of the Great Attractor includes a massive cluster known as the Norma Cluster, along with the sprawling Centaurus cluster complex, all embedded in a dense knot of the cosmic web. The pull we feel is the integrated gravity of this entire hidden metropolis. Yet even as we map it, a deeper question arises. The motion of Laniakea and our local galaxies is so immense that some scientists calculate the mass we have now found behind the zone of avoidance might still not be enough to account for all of it. This suggests the Great Attractor itself may be just the nearest major landmark in a much longer gravitational slope that leads all the way to the even more colossal Shapley Concentration, hundreds of millions of light years farther on. The curtain is being pulled back, not to reveal a single monster, but a highway of mass stretching into the depths of the web, a path we are destined to follow for eons to come. Gravity's push can be as powerful as its pull. For years, we focused on the massive attractors drawing us in, but our motion through the cosmos required another explanation, a force from the opposite direction. Astronomers found it not in a concentration of mass, but in a staggering absence. They named it the dipole repeller. This is the fascinating counterpart to the Great Attractor, a vast, diffuse region of space so empty that its lack of gravity actively shoves us away. Think of it like this: if the Great Attractor is a mountain pulling us uphill, the dipole repeller is a deep valley behind us, its emptiness creating a slope that we slide down. This concept of a repeller is crucial to understanding the bulk flows, those immense rivers of galaxy motion. In the smooth fabric of space-time, mass creates wells that attract, but profound underdensities create gentle hills. Matter naturally flows away from the hills and into the wells. The dipole repeller is one of the largest such hills in our vicinity. It is not a single void like Boots, but likely a complex of connected underdensities, a sprawling cosmic hinterland of very little matter. Its repulsive effect, combined with the attractive pull from the Shapley Concentration and the Great Attractor, perfectly explains the precise direction and speed of our local group's journey. We are in a cosmic tug of war between something and nothing. The local void we discussed earlier, that emptiness right at our galactic doorstep, is now understood to be just a small part of this much larger repelling region. Together, the local void and the dipole repeller form the negative landscape against our backs, while the attractors form the positive landscape ahead. Our path is set by this imbalance. This reshapes our understanding of cosmic dynamics. We are not merely being dragged toward a destination, we are also being expelled from an origin. The nothingness has a shape and a gravitational signature all its own. It means that to chart a galaxy's voyage, you must map the voids as meticulously as you map the clusters. The great attractors define where we are going, but the great repellers tell us where we have been and why we had to leave. The frontier opposite our home supercluster complex is marked by another titan. Known as the Southern Wall or sometimes the Centaurus Wall, this immense structure forms a colossal sheet of galaxies that stands as a southern counterpart to the Pisces-Cetus complex we inhabit. It is a defining border in its own region of space, a dense concentration of mass that helps shape the local flow of the cosmic web. This wall is not an isolated curtain. It is deeply connected to the greatest gravitational landmark in its direction, serving as a major filament feeding directly into the Shapley Concentration. The galaxies within the southern wall are part of the immense river of matter flowing toward that supercluster, acting as a vast catchment area that funnels mass along the web's threads. This interconnection reveals a deeper truth about cosmic architecture. What we often label as separate superclusters or great walls are rarely independent. They are frequently just the densest segments of even larger, interconnected complexes, like mountain ranges that are part of the same continental spine. The southern wall, the Shapley Concentration, and other nearby structures like the horologium, reticulum, supercluster are all linked, forming a metastructure of almost incomprehensible scale. This is the true nature of the cosmic web, a three-dimensional foam where the dense walls of galaxies form the membranes, and the voids form the bubbles within. We are not looking at isolated islands or solitary walls, but at a single, continuous sponge of matter, with filaments intersecting and merging into nodes of staggering density. The southern wall is one such membrane, a vast plane in this foam that channels the universe's mass. Its existence reinforces that the largest patterns we see are not accidents, but the fundamental cellular structure of the cosmos, built by gravity from the quantum ripples of the beginning. What other immense, interconnected complexes lie beyond our current maps, waiting to redefine our understanding of this universal foam? At the heart of a serpentine constellation lies a furnace of cosmic violence. The Ophiuchus supercluster is a dense, sprawling gathering of galaxies located about 390 million light-years away, a place where the cosmic web knots itself into a region of extraordinary density and heat. Within its core sits one of the most massive and dynamic galaxy clusters in the known universe, a behemoth simply called the Ophiuchus cluster. This is not a quiet, settled city of ancient stars. It is a raging inferno, a place where the very space between galaxies is filled with gas heated to over 100 million degrees, glowing so fiercely in X-rays that it outshines the combined light of all the cluster's stars. This scorching intracluster medium is a testament to the violent history of the cluster, shaped by colossal mergers and unimaginable energy releases. It is a supercluster core in its most extreme and active state, a natural laboratory for the most powerful forces in the cosmos, and within this seething heart, astronomers have discovered the scars of past cataclysms on a scale that defies belief. Using radio telescopes, they mapped a pair of immense, bubble-like cavities carved into the million-degree gas. These are radio fossils, the lingering remnants of jets that once blasted from the supermassive black hole at the cluster's center billions of years ago. The energy required to blow these bubbles is beyond staggering, but it was merely a prelude to a far greater discovery. Deeper analysis revealed something even more colossal, a cavity so vast it seemed impossible. Stretching across a mind-numbing 1.5 million light-years, this single structure appears to be the imprint of the largest explosion ever detected in the universe since the Big Bang. The energy release would have been 5 times more powerful than the previous record holder, a blast so titanic it makes the combined output of every star in our galaxy over its entire lifetime seem insignificant. This is not the flash of a supernova or the burst of a gamma ray. It is a slow, seismic eruption that likely lasted for hundreds of millions of years, a sustained roar from a supermassive black hole in a state of unimaginable fury. What could cause such an event? The leading theory points to an epoch of truly monstrous accretion, when the central black hole gorged itself on an immense amount of gas and stars. The resulting jets, focused and relentless, acted like cosmic blowtorches, pushing the hot cluster gas aside and creating a void of truly biblical proportions. The discovery of this fossilized cavity does more than just break records. It fundamentally changes our understanding of the life cycle of the most massive structures in the universe. It tells us that the cores of superclusters are not just places where galaxies gather. They are arenas for energy releases that can reshape the entire cluster environment, halting the formation of new stars in hundreds of galaxies and governing the flow of gas for billions of years. The quiet bubble we see today in the radio data is the echo of a primeval scream, a reminder that the architecture of the cosmos is built not only by gravity's gentle pull, but also by the occasional, universe-shaking shout of pure cosmic power. Centuries of stargazing had given the Centaurus region a legendary status long before we understood why. This sprawling zone of the southern sky, encompassing the constellations of Centaurus and Hydra, held a gravitational secret that would take generations to decode. Early galaxy surveys, even with their limited reach, consistently noted an unusual concentration of galaxies in this direction, a persistent overdensity that hinted at something immense. Astronomers named this apparent structure the Hydra-Centaurus supercluster, marking it as one of the largest known assemblies of matter in our cosmic neighborhood. For decades, it stood on our maps as a distinct continent of galaxies, its heart believed to be the source of the mysterious tug we called the Great Attractor. The Hydra-Centaurus supercluster was our first, best guess at the identity of the hidden giant pulling us through the void. It represented a monumental step in understanding, a recognition that our local universe was not random, but organized around immense gravitational anchors. Yet, as our tools grew sharper, this seemingly settled picture began to unravel. The supercluster was not wrong, but it was incomplete. New three-dimensional maps, built not just from positions, but from the precise velocities of thousands of galaxies, revealed a more fluid and interconnected reality. The galaxies in Hydra-Centaurus were not all moving together as a single, isolated block. Instead, their motions painted a picture of a vast watershed. Some streams flowed toward one gravitational center, others toward a different one. This crucial insight came from analyzing the peculiar velocities, the local deviations from the universal expansion. It showed that the traditional boundaries drawn on static maps were often arbitrary. A galaxy might appear, from its position, to be part of Hydra-Centaurus, but its motion told a different story, revealing it was actually a traveler passing through, or a resident of an entirely different gravitational domain. This velocity-based cartography led to the revolutionary redefinition we now accept. The Hydra-Centaurus supercluster was not a separate entity from our local structure. It was, in fact, the central, densest region of our home supercluster, Laniakea. The Great Attractor lies at its gravitational heart, and the ancient constellations of Hydra and Centaurus trace the core of our immense celestial continent. What we once labeled as a neighboring supercluster was actually the bustling downtown of our own cosmic metropolis. This historical shift is more than a simple name change. It reflects a profound evolution in how we perceive cosmic structure. We moved from seeing the universe as a collection of static islands defined by where galaxies are, to understanding it as a dynamic flow defined by where galaxies are going. The Hydra-Centaurus region remains critically important, not as a destination, but as the powerful engine of Laniakea's gravity, the dense knot that gathers the galactic rivers from hundreds of millions of light-years away. Its history is a testament to our journey of cosmic mapping, a reminder that sometimes, to find our true place in the universe, we must learn to read not just the stars, but the currents they ride. Far from the blazing cores of superclusters, the cosmic web holds quieter, more elusive threads. In the constellation Sextans, a faint and ghostly gathering drifts through the void, a loose aggregation of galaxies known as the Sextans cloud. This is not a great wall or a dense cluster, but a wispy, low-density cloud, a celestial cirrus formation against the dark sky. Its galaxies are not bound tightly by gravity into a single, coherent structure. Instead, they drift in a loose association, a scattered community separated by vast stretches of intergalactic space. Objects like the sexton's cloud represent the faintest, most basic level of cosmic organization, the raw material from which the grander architecture is built, or perhaps the delicate remnants left behind after larger structures have finished forming. Studying these faint clouds is like an astronomer conducting a census of a remote, rural countryside, after having already mapped all the great cities and highways. It completes our picture of the local universe, ensuring we account for every galaxy, not just the bright and obvious ones huddled in dense urban centers. These low-density environments are crucial laboratories for understanding a different kind of galactic life. In the intense gravity of a massive cluster, galaxies are harassed, stripped of their gas, and forced into collisions, rapidly aging them. But in the serene isolation of a cloud like Sexton's, galaxies live quiet, undisturbed lives. They hold onto their reservoirs of cold gas for longer, allowing for slower, more sustained star formation. They are less likely to suffer dramatic mergers, preserving their delicate spiral shapes over billions of years. By comparing the galaxies in the Sexton's cloud to their cousins in the dense Virgo cluster, astronomers can isolate the effects of environment on a galaxy's evolution, seeing what happens when a galaxy is left mostly to its own devices. The very existence of such a loose cloud also poses a question about its origins. Is it a filament in its infancy, a strand of the cosmic web that simply never gathered enough matter to condense into a sharp, dense wall? Or is it fossil debris, the leftover outskirts of a much larger structure that long ago coalesced, its core having drawn away the densest material and left this faint halo behind? The answer helps us trace the history of our local cosmic neighborhood, understanding not just where matter is now, but where it has flowed over the eons. The Sexton's cloud, in its faint and scattered glory, reminds us that the universe's structure is not defined solely by its brilliant metropolises, but also by its wide open spaces and the lonely towns that dot them. To truly understand the cosmic web, we must listen to its quietest whispers as intently as we study its most powerful roars. Another faint congregation drifts through the void near the constellation of the Dove. The Columba Cloud is a sparse, nearby gathering of galaxies, a neighbor to our own local group that reveals a fundamental truth about cosmic structure. Even on these relatively small scales, the distribution of galaxies is not smooth or uniform. It is profoundly patchy. Galaxies do not gradually fade into the emptiness. They cling together in loose, irregular clouds separated by wide gulfs of near-nothingness. This patchiness is the basic fabric of the universe, visible from the colossal walls spanning billions of light-years down to these local, gossamer assemblies just tens of millions of light-years across. Defining where a cloud like Columba begins and ends is one of astronomy's subtle challenges. There is no sharp edge, no wall or membrane. Instead, astronomers must identify a statistical overdensity, a region where the number of galaxies per cubic million light-years is noticeably higher than the background. This is like trying to map a fog bank from within, determining its boundaries by the gradual thinning of the mist. The exact membership of the Columba Cloud is therefore a matter of ongoing study, as new, fainter dwarf galaxies are discovered and their precise distances measured. The cloud's true shape and extent slowly come into focus. These diffuse local clouds are far more than just celestial curiosities. They are critical laboratories for understanding the forces that sculpt the smallest galaxies. Within the quiet expanse of a cloud like Columba, dwarf galaxies evolve under the gentle but relentless influence of tidal forces. These are not the violent, disruptive tides of a massive cluster, but the subtle, persistent tugs from the combined gravity of all the other galaxies in the cloud and from the immense mass of our own local group nearby. Over billions of years, these tidal forces can stretch and distort a dwarf galaxy, pulling stars away to form long, faint streams, or even completely disrupting its structure, transforming it from a coherent sphere into a diffuse smear of stars. By studying the shapes and motions of galaxies within the Columba cloud, astronomers can trace the history of these gentle, gravitational interactions. They can see which dwarfs are being slowly pulled apart and which have survived relatively unscathed, painting a picture of the dynamical history of our local cosmic neighborhood. Furthermore, the kinematics of these clouds, the precise motions of all their member galaxies, provide a vital map of the local volume's gravitational landscape. The way the Columba cloud moves as a whole, and how its individual galaxies move within it, tells us about the total mass distribution in our vicinity, including the unseen influence of dark matter. It is a detailed motion study that reveals the subtle pushes and pulls from all the nearby structures, from the great attractors ahead to the repelling voids behind. In its faint, scattered form, the Columba cloud acts as a sensitive instrument, its galaxies like buoys on a cosmic sea, bobbing in response to currents of gravity too faint for us to perceive directly. Understanding this cloud is essential to charting the full gravitational field that guides not only its own fate, but the long-term trajectory of our Milky Way as well. Mapping the universe's largest structures demands a cosmic perspective, a clear distinction between the distant and the local. But what happens when a strange signal appears in our own galactic backyard, blurring that line entirely? Just beyond the familiar spiral arms of the Milky Way, in the direction of the constellation Canis Major, lies a dense, mysterious cloud of stars. This is the Canis Major overdensity, and its true nature has sparked a quiet but intense debate among astronomers. Is it a dwarf galaxy in the process of being torn apart by our Milky Way's immense gravity, or is it merely a spectacular tidal stream, a river of stars ripped from a smaller galaxy long ago and now wrapped around our own? The answer matters deeply, because it changes how we interpret the shadows and glimmers we see across the cosmos. When we peer into deep space, searching for the Great Walls and Superclusters, we must first be certain that the smudges of light we detect are not just local debris, but true islands in the distant void. The Canis Major overdensity is a perfect case study in this fundamental challenge of cosmic cartography. From our vantage point inside the Milky Way, it appears as a significant concentration of stars, particularly ancient, metal-poor red giants. If it were a dwarf galaxy, it would be one of our closest galactic neighbors, a satellite being actively shredded and consumed. Its stars would have formed together in their own distinct system before being captured. If, however, it is a tidal stream, then these stars are not native to each other. They are refugees from another galaxy, now strung out along a vast orbit, their shared motion the only thing linking them. Distinguishing between these two possibilities requires exquisite three-dimensional mapping. Astronomers must measure not just the positions of these stars, but their precise distances and, most importantly, their velocities through space. Do they move as a coherent, bound system, or as a long, flowing line? The evidence remains tantalizingly ambiguous. Some studies suggest a degree of coherence that hints at a dwarf galaxy core. Others point to the elongated, stream-like distribution of the stars, arguing it is purely the debris of a past encounter. This uncertainty is not a failure of observation, but a reflection of the messy, dynamic process of galaxy growth itself. The Milky Way is not a static island. It is a cannibal, continuously absorbing smaller galaxies and stitching their stars into its halo. The Cain's major overdensity may be a snapshot of this process, a structure caught in the act of being dismantled. So when we look out and see a faint smudge of light billions of light years away, could it, too, be a similar puzzle? Could some of the faint overdensities we attribute to distant superclusters actually be complex tidal debris around a foreground galaxy we have not fully mapped? This local mystery reminds us that the universe is layered, and to see its grandest designs, we must first learn to recognize the architecture of our own home. For much of the 20th century, our cosmic address was written with a single, grand title, the Virgo Supercluster. This was the map we grew up with, a comforting picture of cosmic hierarchy. In this model, our Milky Way and its local group were just a quiet suburb on the outskirts of a vast continent of galaxies, all orbiting a brilliant, dense core, the mighty Virgo cluster. This cluster, containing over 1,000 galaxies, was seen as the gravitational heart of our entire region, the sun around which our galactic neighborhood revolved. It made intuitive sense, a central city with sprawling suburbs, and it defined textbooks for generations. Our place in the universe felt settled, mapped, and understood. We were residents of a known supercluster, with Virgo as its capital. But this elegant model had a critical flaw. It was based primarily on a snapshot, a static map of where galaxies appeared to be in the sky. It did not fully account for how they were moving. The revolution came with precision, as astronomers developed more sophisticated tools to measure not just the positions of galaxies, but their precise distances and, most importantly, their three-dimensional motions through space. The old picture began to dissolve. They could now subtract the uniform expansion of the universe and see the peculiar velocities, the individual drifts caused by local gravitational tugs. When they applied this to the galaxies in and around the Virgo supercluster, they discovered something astonishing. The galaxies were not all orbiting Virgo in a grand, unified dance. Instead, their motions painted a far more dynamic and expansive portrait. Some streams flowed toward Virgo, yes, but others seemed to be passing by, and still others were moving in concert toward a point far beyond it. The Virgo cluster was not the ultimate gravitational destination. It was a major waypoint, a dense knot in a much larger river system. This velocity-based cartography revealed the true boundaries of structure, not by density alone, but by flow. It showed that what we called the Virgo supercluster was actually just the densest local part of an immense continent we now call Laniakea. Virgo remains immensely important, of course, but its role shifted from capital city to a major metropolitan hub within a vast nation. This evolution from the Virgo-centric model to the Laniakea watershed is a profound lesson in scientific humility. It demonstrates how our understanding of the cosmos deepens not by discarding old ideas, but by refining them with better data. We did not leave the Virgo supercluster behind. We simply discovered the full continent it belongs to. Our maps grew larger, and in doing so, they revealed a universe where motion defines destiny, and where every galaxy, even in a cluster of thousands, is part of a journey far greater than we ever imagined. Journey far to the south, beyond the familiar stars of the Milky Way, to the constellation of the Crane, Grus. Here, at a staggering distance of over 4 billion light-years, we find a dense gathering of mass known as the Grooves Cluster. This is not a nearby structure, but a window to a younger, more dynamic universe. We see it not as it is today, but as it was when our solar system was just beginning to form, a snapshot of cosmic adolescence. The cluster itself is a rich metropolis of galaxies, but its true significance lies in its connection to the wider cosmic web. The Grooves Cluster is not isolated. It is anchored at the intersection of several faint, sprawling filaments of galaxies, threads of matter that stretch into the surrounding darkness. This distant cluster and its filamentary connections are a crucial time capsule for astronomers. By studying such structures at high redshift, meaning we see them as they were billions of years in the past, we can perform a direct test on our theories of cosmic evolution. How quickly did these immense walls and nodes assemble? Was the cosmic web fully formed in the early universe, or was it a ragged, under-construction site? The Grooves filament provides clues. By mapping the galaxies along its length and measuring their speeds, astronomers can determine if this filament was already a coherent, flowing highway of matter back then, or if it was still a loose collection of clouds just beginning to feel gravity's pull. Furthermore, the dense environment of the Grooves Cluster itself acts as a laboratory for galactic evolution. We can compare the galaxies trapped in its dense, hot core to those still residing in the quieter filament. In the cluster's fierce gravitational grip, galaxies are harassed, stripped of their star-forming gas, and forced into mergers, rapidly transforming spiral disks into featureless elliptical galaxies. Out in the filament, the process is slower, more gentle. By studying this contrast in a single, distant system, we see the environmental forces that shape galactic destiny playing out in real time, across cosmic history. The light from Grooves has been traveling for so long that it shows us the universe during its most formative era, allowing us to watch the cosmic web being woven and to understand how a galaxy's address within it determines its entire life story. The universe is a sculptor of extremes, carving both dense cities of light and deserts of perfect dark. Just such a stark frontier exists in the southern constellation of Telescopium. Here, a modest gathering of galaxies known as the Telescopium group sits in profound isolation, not because it is alone in the universe, but because it borders one of the great silent chambers of the cosmic web. This group is a textbook node, a local knot of gravity where a few dozen galaxies, including our own Milky Way's smaller cousins, are bound together in a gentle dance. But turn your gaze just beyond this island community, and you encounter the Telescopium void, a sprawling spherical region of emptiness that stretches for hundreds of millions of light years. The transition is not gradual. It is a cliff edge in the distribution of matter, a sharp boundary where the cosmic web's luminous filaments simply end, giving way to an immense, lightless interior. This dramatic juxtaposition is not a cosmic accident. It is a fundamental feature of how gravity structures the universe. The group and the void are two sides of the same gravitational coin, born from the same ancient processes but destined for opposite fates. To understand why such sharp contrasts exist, we must follow the flow of matter over billions of years. One compelling theory that explains the emptiness of voids like this one is called void sweeping. Imagine the cosmic web as a vast watershed during a heavy rain. The water, representing galaxies and intergalactic gas, does not fall evenly. It gathers into rivulets, then streams, then mighty rivers, all flowing downhill into lakes and oceans, the great clusters and superclusters. The land between these waterways drains, becoming dry and barren. In the cosmos, gravity is the slope that everything flows down. Over eons, even the faintest wisps of matter within a proto-void feel the gentle, persistent tug of the denser regions at its edges. This creates a slow but relentless evacuation. Galaxies on the void's fringes are pulled outward, joining the filaments. Vast clouds of hydrogen gas, the raw material for future stars, are siphoned away. The void itself expands and empties further, its own growth accelerating as the universe expands, stretching its emptiness even thinner. The telescopium group, then, might be seen as a piece of debris left on the shoreline of this retreating sea, a last outpost of matter that hasn't yet been swept into the denser currents. Or perhaps it is a small, self-contained system that formed early on, stable enough to resist being pulled apart, but not massive enough to draw other material to it. Its existence right on the void's edge highlights the violent quiet of this process. Void sweeping is not a cataclysm. It is a slow-motion desertification of space, leaving behind regions so clean and empty that they become the purest examples of nothingness in the known universe. This dynamic explains why voids are not just randomly scattered empty spots, but coherent, often spherical bubbles within the web's foam-like structure. Their shapes are carved by the outward pressure of surrounding matter, like bubbles in a pan of soap solution pressed together by their neighbors. Looking at the telescopium region, we see a frozen moment in this billion-year process, a snapshot of the cosmic web's relentless sorting of matter into light and shadow, presence and absence. Deep in the southern celestial hemisphere, a dense archipelago of galaxies defines another gravitational landmark. The Indus supercluster, while not the closest of these structures, stands out for a remarkable characteristic. It contains an unusually high number of what astronomers term rich clusters. These are not just casual gatherings of a few dozen galaxies, but immense, densely packed cities, each hosting thousands of galactic members bound in a ferocious gravitational embrace. This concentration of massive clusters within a single supercluster makes the Indus region a powerhouse of gravity, a significant knot in the cosmic web that exerts a commanding pull on the galaxies and intergalactic gas for hundreds of millions of light-years around it. Its influence contributes to the complex river of motion in that sector of the universe, subtly altering the paths of other superclusters and filaments, adding its own note to the symphony of large-scale flows. But mapping a distant supercluster like Indus is about far more than just cataloging its luminous cities. It is a forensic exercise in weighing the invisible. The sheer existence and stability of these colossal clusters present a direct challenge. The visible matter we see, all the stars and glowing gas, is simply not enough to hold them together. The galaxies within a rich cluster are moving at tremendous speeds, thousands of kilometers per second. If only the gravity from the visible stars was at work, these galaxies would have flown apart long ago, scattering into the void. Something else, something that does not emit or reflect light, must be present in vast quantities to provide the extra gravitational glue. This is the elusive signature of dark matter. By carefully studying the motions of galaxies within the Indus supercluster's clusters, astronomers can perform a cosmic weigh-in. They measure how fast the galaxies orbit the cluster's center, and from those speeds, they calculate the total mass required to keep them bound. The result always far exceeds the mass of all the visible stars and gas. The difference is the dark matter halo, an immense, invisible sphere of unknown particles that cradles the entire cluster, dictating its shape and holding its structure together over billions of years. Every distant supercluster we map like Indus, becomes another data point in this grand investigation. By tracing the distribution of these luminous nodes, we are indirectly tracing the underlying scaffolding of dark matter upon which they formed. The cosmic web we see in light is merely a luminous tracing along the contours of a much vaster, unseen architecture. The dense clusters of the Indus supercluster are like bright lamps hanging in a dark forest, their positions revealing the hidden branches of the tree that holds them up. Far to the north, the cosmic web traces a long, graceful arc through the constellation of the Water-Bearer. This is the Aquarius supercluster, a sprawling filament of galaxies that presents itself not as a dense, spherical knot, but as an elegant, elongated chain stretching across the void. Its structure is a classic example of a supercluster in its most filamentary form, a river of galactic cities and towns connected by threads of gravity. Within this vast celestial highway, astronomers have found a perfect natural laboratory to answer a fundamental question: how does a galaxy's address within the cosmic web determine its fate? To find the answer, they have turned detective, examining the shapes of the galaxies themselves. Every galaxy tells a story in its form. Spiral galaxies, like our own Milky Way, are flat, rotating disks of stars, gas, and dust, often with beautiful, star-forming arms. They are vibrant, youthful places where new stars are constantly being born. Elliptical galaxies, in contrast, are generally round or oval-shaped blobs of older, redder stars, with little gas or dust left to fuel new star formation. They are cosmic retirement homes, their star-making days largely over. By cataloging whether spiral or elliptical galaxies dominate different neighborhoods within the Aquarius filament, scientists can read the environmental history written in starlight. What they discover is a clear and telling gradient. In the densest nodes of the supercluster, where galaxy clusters intersect and crowd together, elliptical galaxies reign supreme. The environment here is intense and violent. Galaxies swing past each other at high speeds, their gravitational fields interacting in a chaotic dance. The thin gas that fuels star formation is often ripped away by these encounters or heated to extremes by the fierce pressure of the intracluster medium. This process, called ram pressure stripping, effectively starves a spiral galaxy, shutting down its star-forming factories and leaving it to age into a smooth, red, elliptical shape. Mergers are also common in these crowded urban centers, and when two spiral galaxies collide, they often produce a single, larger elliptical galaxy as a result. Now, travel out from these dense urban cores along the quieter suburban stretches of the Aquarius filament. Here, the galaxy population shifts dramatically. Spiral galaxies become far more common. In these less crowded environments, galaxies are spared the constant gravitational harassment and the searing heat of dense gas. They can hold onto their reservoirs of cold gas for billions of years, allowing them to maintain their delicate disk structures and continue forming new stars at a gentle, steady pace. They are islands of relative calm within the flowing river of the filament. This morphological segregation is a powerful clue to the life cycle of cosmic structure. It shows that the transformation of a galaxy from a star-forming spiral into a quiescent elliptical is not just a matter of its internal clock. It is driven powerfully by its surroundings. A galaxy born in a dense cluster node may be destined for an early retirement, its evolution accelerated by the bustling metropolis it calls home. A galaxy born in a faint, outlying thread of the same supercluster may live a long, quiet, and productive life, its spiral arms turning for eons. The Aquarius supercluster, in its great length, allows us to see this entire spectrum in one connected system. It demonstrates that the cosmic web is not just a map of where things are. It is a timeline of transformation, where the very architecture of space writes the biography of every galaxy within it. Distance itself can be the final frontier, not just of space, but of certainty. Far beyond the well-mapped territories of Laniakea and Shapley, in the faint constellation of the Chisel, lies the Calum supercluster. It is a ghost on the edge of our vision, a sprawling assembly of galaxies so distant that its light has been traveling toward us for well over 1 billion years. Observing a structure like this is not like looking at a nearby wall, sharp and clear. It is more like trying to discern the shape of a distant mountain range through a thick, shifting haze. The challenges are immense and fundamental, rooted in the very techniques we use to map the cosmos. The first and most persistent problem is foreground contamination. Between us and the Calum supercluster lies an ocean of cosmic clutter, countless stars from our own Milky Way, nearby dwarf galaxies, and faint, unrelated clouds of dust and gas. These objects are not part of the supercluster, but they are superimposed on it in our two-dimensional view of the sky. Distinguishing which faint smudge of light belongs to the distant supercluster and which is a local star or a foreground galaxy is a painstaking, pixel-by-pixel detective game. A single misidentified object can warp our entire perception of the structure's size and shape. The second, even trickier challenge is the uncertainty of redshift. Redshift is our primary tool for measuring cosmic distances. The farther away a galaxy is, the faster it appears to be receding from us due to the expansion of the universe, and the more its light is stretched or redshifted. For a supercluster like Calum, we measure the redshifts of hundreds of its member galaxies to build a three-dimensional map. But redshift is not a perfect ruler. A galaxy's motion is not purely due to cosmic expansion. It also has a peculiar velocity, a local drift caused by the gravitational tug of its neighbors. Within a dense supercluster, these peculiar velocities can be significant, thousands of kilometers per second. This means a galaxy's redshift gives us a distance that might be off by tens of millions of light years. When you combine these small errors across hundreds of galaxies in a vast, faint structure, the entire supercluster can appear blurry and indistinct in our maps. Is that gap a true void within Calum, or just a region where galaxies with large, peculiar velocities have been misplaced in our three-dimensional reconstruction? The answer is often elusive. This is why Calum represents a frontier. It is not just a place on a map, it is a test case for the limits of our current technology. To see it clearly, to trace the true contours of its filaments and measure the mass of its clusters, we need a new generation of eyes on the sky. This is the promise of upcoming observatories like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope. Their power lies in sheer, breathtaking volume. They will not study a few hundred galaxies in the Calum region. They will survey millions. This vast statistical sample will wash away the noise of foreground contamination and smooth out the uncertainties of peculiar velocities. By mapping the precise positions and subtle shapes of billions of faint galaxies across the entire sky, these telescopes will trace the underlying dark matter scaffolding of the universe with unprecedented fidelity. The faint, ghostly outline of Calum will snap into sharp focus, revealing whether it is a simple filament, a complex knot, or perhaps the anchor for an even larger structure we cannot yet see. Completing this map of our cosmic neighborhood, out to these distant frontiers, is about more than just cataloging another supercluster. It is about testing the fundamental rules of cosmic architecture. Does the web look the same in the distant, younger universe as it does nearby? Are the filaments in Calum as well defined as those in Perseus Pisces, or are they fuzzier, hinting at a time before gravity had fully sculpted the matter? By finally bringing structures like the Calum supercluster into clear view, we will be completing the census of the local universe, filling in the last blank spaces on the greatest three-dimensional map ever attempted. Only then can we truly know if the patterns we see around us, the walls, the voids, the great flows, are universal, or if we have merely been reading the first page of a much longer and more mysterious story. The southern constellation of Phoenix holds not a mythical bird reborn from ashes, but a different kind of cosmic rebirth entirely. Here, at a distance of nearly 6 billion light-years, lies the Phoenix supercluster, a sprawling, ancient metropolis of galaxies. We see it as it was when the universe was less than half its current age, a time of immense energy and furious construction. For astronomers, this supercluster is a cornerstone, a vital benchmark in the deep southern sky. Its discovery and detailed mapping were pivotal, because the southern celestial hemisphere had long been a relative terra incognita compared to the north. Major surveys like the Sloan Digital Sky Survey had painted a magnificent portrait of the northern cosmos, revealing great walls and voids, but the south remained a fainter, less charted territory. The Phoenix supercluster became a key landmark in this southern frontier, a bright, dense signpost that helped anchor our understanding of structure across the entire sky. Its properties are not just interesting, they are essential calibration tools. Scientists use superclusters like Phoenix as cosmic measuring sticks to test and refine the supercomputer simulations that recreate the universe's evolution. These simulations, which model how dark matter and gas clump together under gravity from the Big Bang to the present day, produce virtual universes. But how do we know if these digital cosmoses are accurate? We compare them to real ones. This is where the specific, measurable properties of a supercluster like Phoenix become invaluable. Astronomers look at its cluster richness, how many massive galaxy clusters it contains within its boundaries. They measure the separation between these clusters, the typical distances that define the supercluster's internal architecture. They analyze the overall shape. Is it a tight, spherical knot, or a more elongated filament? All of these are quantifiable features. Researchers then sift through their simulated universes, searching for virtual superclusters that match Phoenix's profile, its richness, its separation, its shape. When they find a close match, it tells them that the physics and the initial conditions baked into that simulation are likely correct. It is a process of cosmic pattern matching. If no simulation can produce a structure quite like Phoenix, it is a red flag, a sign that our models might be missing a crucial ingredient, whether in the nature of dark matter, the influence of dark energy, or the behavior of primordial gas. Furthermore, because we see Phoenix in the distant past, it offers a snapshot of a supercluster during its most active period of assembly. Studying its galaxy populations tells us how quickly such immense structures came together. Were its galaxies already old and red, or were they still blue and vigorously forming stars? The answers help us timeline the maturation of the cosmic web. So the Phoenix supercluster is far more than a distant collection of galaxies. It is a standard candle for cosmic structure, a reference point against which we measure our theories of how everything, from the smallest filament to the largest wall, is built. In its ancient light, we find the rules for constructing a universe. Another faint and sprawling cloud drifts through the southern sky, a quiet neighbor in our local cosmic sea. The Tucana cloud is a diffuse, nearby gathering of galaxies, a close relative to the Columba and Sextans clouds we have already encountered. Its galaxies are not bound into a tight cluster, but form a loose association, a scattered archipelago separated by millions of light years of near emptiness. Yet within this apparent randomness lies a powerful tool, a key to unlocking the invisible forces that guide everything in our corner of the universe. The true value of studying the Tucana cloud is not in its visible stars, but in their motion. By meticulously measuring the velocities of its member galaxies, astronomers can trace the subtle currents of gravity that flow through our intergalactic neighborhood. Each galaxy in the cloud has a two-part motion. The first is the general expansion of the universe, carrying it outward on the cosmic tide. The second, more telling component is its peculiar velocity, the local drift caused by the gravitational tug of all the surrounding mass, both seen and unseen. The Tucana cloud, as a cohesive group, has its own bulk motion through space. By charting this motion and comparing it to our own local group's journey, scientists can map the gravitational relationship between these two nearby structures. Are we moving together, pulled by the same distant attractors, or are our paths diverging, suggesting different gravitational influences at play? The answers create a vector map of local flows. This kinematic data transforms the Tucana cloud from a simple collection of galaxies into a sophisticated tracer particle for the gravitational potential field. Think of it like dropping a handful of buoys into a wide, dark ocean. By watching how they drift and cluster, you can infer the hidden currents and tides below the surface, even if you cannot see the water itself. In the cosmic ocean, those hidden currents are shaped by the distribution of dark matter, the gentle but relentless pull that guides the Tucana cloud's trajectory is not just from the galaxies we can see in Virgo or the Great Attractor. It is the integrated gravity of the entire local mass distribution, dominated by the vast, invisible halos of dark matter that envelop every galaxy group and filament. By modeling how the Tucana cloud moves, astronomers can work backwards. They can create a mathematical map of the gravitational landscape required to produce that motion. This map reveals where the unseen mass must be concentrated to tug on the cloud in the precise way we observe. It helps to constrain models of the dark matter halo that surrounds our own local group, and it defines the shape of the local gravitational well we all inhabit. In this way, a faint, scattered cloud of galaxies becomes a precision instrument. Its kinematics are a whisper that tells us about the architecture of darkness, helping to outline the invisible skeleton upon which our entire local universe is built. Stretching across the southern celestial sphere, a great arch of galaxies connects two brilliant constellations. The Pavo-Indus supercluster forms a majestic, elongated bridge between the Peacock and the Indian, a filament of such scale it defies our earthly sense of geography. This is not a dense, spherical knot of matter, but a sweeping river of galactic groups and clusters, a structure that embodies the true meaning of the cosmic web. Its shape tells a story of connection, not isolation. On one end, it links with the immense gravitational influence of the Indus supercluster, with its rich, dense clusters. On the other, it reaches toward the sprawling Pavo region. This supercluster does not exist in a vacuum. It is a vital strand in a larger tapestry, a highway of matter that channels galaxies and intergalactic gas between these two major overdensities. To visualize it, think of a great mountain range connecting two major continents. The range itself has its own peaks and valleys, dense clusters, and quieter groups, but its true purpose is to provide the land bridge between the massive landmasses on either side. The Pavo-Indus supercluster functions in exactly this way for the cosmic landscape. Its elongated form is a direct result of the gravitational dynamics that built our universe. In the early cosmos, matter did not collapse into neat, isolated spheres. Instead, it flowed along the lines of an invisible dark matter scaffold, condensing into filaments where these lines intersected. The Pavo-Indus structure is one of these primordial filaments, seen at a scale of hundreds of millions of light years. The galaxies within it are not randomly scattered. They are aligned along this invisible backbone, tracing the path of least resistance through the gravitational landscape. This interconnectedness has profound implications. It means that a galaxy's journey is rarely a straight line into the nearest cluster. A galaxy might form in a quiet part of the Pavo-Indus filament, then slowly, over billions of years, be drawn along this celestial roadway, passing by other groups, before finally being delivered into the dense urban core of the Indus supercluster. The supercluster is the conduit for this migration. Furthermore, its interactions are not limited to its endpoints. The gravitational field of such a long, massive structure bends the paths of other, smaller filaments and clouds in its vicinity. It can act as a gravitational lens, subtly distorting the light from galaxies billions of light years behind it. It contributes to the local velocity fields, adding its own gentle tug to the complex river of motions in this sector of the universe. The Pavo-Indus supercluster shatters any lingering illusion of cosmic structures as isolated islands. It is a living demonstration that the universe is a continuous, woven fabric. There are no true edges, only transitions, where one filament merges into another, or feeds into a node, which then sends out new filaments in other directions. We label it with two constellation names for our own convenience, but in reality, it is just one segment of a boundless, three-dimensional network, a single thread in a tapestry that has been under construction since the first moments of time. Away from the crowded southern complexes, a northern giant stands in quiet contrast. The Lyra supercluster arcs through its namesake constellation, a vast filament of galaxies that offers a crucial counterpoint to the dense attractors we have mapped in the opposite half of the sky. Its placement is both a challenge and an opportunity, lying frustratingly close to the obscuring plane of our own Milky Way. This galactic zone of avoidance, a band of dust and stars, slices across its territory, threatening to hide entire sections of this immense structure from our optical view. Yet this very obstacle makes its study essential. To claim we understand the universe's architecture, we cannot simply map the easy, clear patches. We must also learn to see through the fog. This northern supercluster's value lies in its role as a balancing weight on the cosmic scale. For decades, our deepest, most comprehensive surveys of large-scale structure have had a southern bias. Pioneering projects like the Sloan Digital Sky Survey, which revealed the Sloan Great Wall, focused on the northern celestial hemisphere. More recent, powerful southern surveys are now catching up, mapping the Shapley Concentration and the southern walls in unprecedented detail. The Lyra supercluster sits squarely in the north, providing a critical data point for comparison. By meticulously studying its size, its mass, and the arrangement of its galaxies, we can perform a profound check on one of cosmology's bedrock assumptions: isotropy. Isotropy is the principle that the universe, on the largest scales, looks the same in every direction. There should be no preferred axis, no giant feature that makes one hemisphere fundamentally different from another. If the South is dominated by a staggering concentration like Shapley, does the North possess a structure of comparable scale and mass to balance it? Or would we find the cosmic web is lopsided, hinting at a primordial asymmetry written into the fabric of space itself? The Lyra supercluster is a key piece of this puzzle. Its properties help us answer whether the great walls and voids are distributed evenly, like the cells in a uniform foam, or if the universe has a grain, a directional preference imprinted at its birth. To peer through the Milky Way's veil, astronomers employ a suite of tools beyond visible light. They turn to infrared satellites, whose longer wavelengths cut through the dust, and to radio telescopes that listen for the faint emission of hydrogen gas from hidden galaxies. They also use statistical reconstruction, carefully modeling how the visible parts of the supercluster likely continue behind the obscuration, based on the gravitational influence they exert on galaxies we can see. This painstaking work is like charting a mountain range when clouds cover the central peaks. You map the foothills on either side and infer the hidden summit that must connect them. What emerges is a portrait of a significant, filamentary supercluster, a northern counterpart to structures like Perseus Pisces. Its existence and general properties so far support the idea of an isotropic cosmos. There is no shocking, universe-spanning wall in Lyra that has no southern equivalent, nor does the north appear as a vast, empty desert compared to the crowded south. This is a profound, if quiet, validation. It suggests that while individual structures like Shapley are extreme, they are not unique. The underlying processes of structure formation operate with statistical fairness across the entire sky. The universe's blueprint, written in dark matter and gravity, appears to have no favorite direction, yet the work is never finished. Each new, deeper survey adds galaxies to the map, refining the boundaries of Lyra and similar northern structures. The quest is to achieve a truly full sky census, where the maps of the north and south are equally deep and precise. Only then can we say with absolute confidence that the grand tapestry is woven from a consistent thread. Any remaining asymmetry, any persistent difference in the clustering patterns between hemispheres would be a seismic discovery, pointing to a flaw in our standard model or a relic of a more exotic beginning. For now, the Lyra supercluster stands as a sentinel in the north, its measured normality a reassuring sign that our cosmic perspective, though limited, is not fundamentally skewed. The northern sky holds a ghostly continent of its own, a sprawling assembly of mass known as the Draco supercluster. Unlike the graceful arc of Lyra, Draco presents itself as a more complex and dense gathering, a supercluster built not from a single, clean filament, but from the interconnection of several massive galaxy clusters, each one a famous landmark in the cosmic atlas. These are the Abell clusters, catalogued by astronomer George Abell in his pioneering survey of the heavens, and within Draco, they form the glittering, dense cities of this northern continent. Clusters like Abell 2256 and Abell 2255 are not mere collections of stars. They are seething metropolises where thousands of galaxies orbit a common center of gravity, bound together by a force far greater than their visible light suggests. To truly weigh these giants, to understand the scale of the gravitational wells they create, astronomers must look beyond the stars to the space between them. The voids within a galaxy cluster are not empty. they are filled with a thin, incredibly hot gas known as the intracluster medium. This gas is heated to temperatures of tens of millions of degrees, so hot that it does not glow in visible light, but instead emits a powerful, penetrating form of energy, X-rays. By pointing space-based X-ray telescopes like Chandra or XMM Newton at the heart of Draco's Abell clusters, scientists can capture this faint, high-energy glow. What they see is a map of the invisible. The hot gas fills the cluster's gravitational well like water in a bowl, tracing its shape perfectly. The distribution and temperature of this gas are direct tracers of the cluster's total mass. Think of it like this: you cannot see the wind, but you can watch how it shapes the clouds and bends the trees. In a galaxy cluster, the galaxies are the trees, and the X-ray emitting gas is the cloud, both shaped by the unseen force of gravity. The hotter and more concentrated the gas, the deeper and more massive the gravitational well that contains it. In Draco's clusters, the X-ray observations reveal profound depths. The gas is not just hot, it is often shaped into complex structures, with shock fronts and cavities carved by jets from supermassive black holes or by the slow, cosmic collisions of clusters merging together. These features tell a story of a violent, dynamic history, a supercluster that is still actively assembling itself. By measuring the properties of this glowing gas, astronomers can perform a precise cosmic weigh-in. They calculate that the visible galaxies account for only a tiny fraction of the total mass, perhaps 15%. The hot gas accounts for another significant portion, but even when combined, it is not enough. The majority of the mass holding the Draco supercluster together, the true source of its immense gravitational pull, is the invisible halo of dark matter. This X-ray vision transforms our understanding of such structures. We no longer see a supercluster as just a collection of points of light in a telescope. We see it as a colossal, three-dimensional landscape of gravity, where brilliant galaxies are merely the tips of mountains whose true bulk lies hidden in the dark, their foundations traced by the faint, million-degree glow of trapped gas. It is a reminder that the universe's greatest structures are defined not by what shines, but by what binds. North of the celestial pole, a great northern emptiness mirrors the profound silence of Bootes. The Camelopardalis void, named for the constellation of the giraffe it occupies, is another of the universe's immense spherical chambers, a region hundreds of millions of light years across where galaxies are astonishingly scarce. Its discovery confirmed a pattern. These titanic voids are not rare accidents, but standard features in the architecture of the cosmos, the empty bubbles in the universal foam. Yet within this and every great void, there exists a fascinating exception to the rule, a handful of isolated galaxies that did not get swept into the cosmic web's dense filaments. These are the void galaxies, and their lonely existence offers a unique window into a different kind of galactic life, one defined by profound isolation rather than constant interaction. Comparing Camelopardalis to the more famous Bootes void reveals subtle but important differences. While both are colossal underdensities, their internal populations are not identical. Bootes is famously, almost eerily, empty, with perhaps only 60 galaxies found in a volume that should contain thousands. Camelopardalis, while still vastly underdense, appears to have a slightly higher population of these isolated systems. This variation is crucial. It tells astronomers that voids are not all the same. They have their own internal structure and history. Some may be older, having had more time to evacuate matter toward their edges, while others might be the result of several smaller voids merging, a process that could leave behind a few stranded galactic islands in the newly formed supervoid. The specific number and arrangement of galaxies within camelopardalis help cosmologists test their models of void formation and evolution, fine-tuning our understanding of how nothingness itself grows and changes over time. But the true scientific treasure within voids like camelopardalis is not their emptiness, but the rare galaxies that stubbornly persist within it. A void galaxy is an island universe in the most literal sense. Separated from its nearest neighbors by tens of millions of light-years of near-perfect vacuum, it evolves in a state of serene solitude. This isolation has profound consequences for its life cycle. In the dense urban cores of galaxy clusters, a galaxy's fate is violent and accelerated. It is subjected to constant gravitational harassment from near misses. Its life-giving cold gas is stripped away by the searing heat of the intracluster medium, and it faces the looming threat of catastrophic mergers. These processes rapidly shut down star formation, leaving behind red, dead elliptical galaxies. A void galaxy knows none of this chaos. It is a cosmic hermit. With no nearby giants to steal its gas or distort its shape, it can hold onto its vast reservoirs of pristine hydrogen for billions of years longer. This means its star-forming factories can remain open for business far into cosmic middle age. Void galaxies are often gas-rich, blue, and actively forming new stars, their spiral arms shining with the light of young stellar nurseries. They are living fossils, preserving a slower, more gentle mode of galactic evolution that was once common in the early universe, before gravity gathered most matter into the crowded web. Their slow, undisturbed lives allow them to grow at their own pace, often resulting in surprisingly large and well-ordered spiral disks. Studying a void galaxy is like finding a secluded village that has maintained ancient traditions untouched by the wars and upheavals of the outside world. Its structure, its chemistry, and its star formation history tell the story of what a galaxy becomes when it is left entirely to its own devices. This radical difference in environment creates a natural laboratory. By comparing a void galaxy from camelopardalis to a similar-sized galaxy in the Virgo cluster, astronomers can directly observe the effects of cosmic location. They see how the cluster galaxy has been stripped of its gas and had its star formation quenched, while the void galaxy remains flush with fuel and vitality. This contrast is the clearest evidence we have that a galaxy's destiny is not written solely at its birth. It is continuously authored by its address in the universe. The great voids, therefore, are not just empty spaces to be skipped over on our maps. They are essential preserves, safeguarding a population of galaxies that follow an alternate evolutionary path. In the deep quiet of the camelopardalis void, the universe quietly conducts a long-term experiment, showing us what happens when a galaxy is given the rarest gift of all, peace. Winter skies reveal a faint, sprawling river of galaxies bridging the constellations of Gemini and Monoceros. This is the Gemini Monoceros cloud, a nearby filament of the cosmic web so close that we can see its faintest, most elusive inhabitants. Its proximity transforms it from a distant smudge of light into a detailed census tract, a place where we can finally take a complete inventory of all the matter, bright and dim, that weaves the universe's grand tapestry. Unlike the brilliant cores of distant superclusters, where only the largest galaxies stand out, this local filament allows our telescopes to peer into the shadows, to detect the myriad dwarf galaxies that would otherwise be invisible across vast distances. These are the cosmic equivalent of small towns and isolated homesteads, the most common type of galaxy in the universe, yet also the hardest to see. They are the fundamental building blocks from which all larger galactic cities were assembled over billions of years. By meticulously counting every single one we can find in the Gemini Monoceros cloud, astronomers are conducting a critical test. Our leading theories of cosmic structure, powered by supercomputer simulations, make a specific prediction about how many of these small galaxies should exist within the low-density environment of a filament. The simulations show a dark matter scaffold, and along its faint threads, they predict a certain population of small, faint galaxies tracing the invisible architecture. But is that prediction correct? For a long time, we simply did not have the data to know. Our surveys of distant structures were inherently biased, only catching the bright, giant galaxies and missing the countless faint dwarfs. This created a potential blind spot in our understanding, a mismatch known as the missing satellites problem, where our models predicted more small galaxies around large ones than we could actually see. The Gemini Monoceros cloud offers a way to test this in a different environment, not around a giant galaxy, but within the quiet expanse of a filament. Here, we can search for the dwarfs free from the blinding glare of a massive neighbor. The results are illuminating. As our surveys grow deeper, we are finding them, these faint, diffuse smudges of stars, each containing perhaps only a few million suns. Their sheer numbers, now becoming visible, are starting to align with the theoretical predictions. Every new dwarf galaxy catalogued in this cloud is a data point that helps verify the underlying rules of the simulation. It tells us that the dark matter scaffold likely exists as modeled, and that the process of seeding galaxies, big and small, along its threads follows a predictable pattern. This local filament, therefore, acts as a calibration site. By getting the census right here, in our backyard, we gain confidence that we understand the basic population statistics of the entire cosmic web. It assures us that when we look at a faint, distant filament and see only a few bright points of light, we can infer the true, much richer population of unseen dwarfs that must accompany them, tracing the full, magnificent structure hidden in the dark. The zodiac holds more than just astrological signs. It contains entire continents of galaxies. Among them, in the faint constellation of Cancer, lies a sprawling assembly of mass known as the Cancer Supercluster. This structure does not boast the extreme density of the Indus region or the filamentary grace of Aquarius. Instead, it serves as a vital benchmark, a textbook example of a moderately rich supercluster. Its clusters are not the most massive, and its filaments are not the longest, but that is precisely what makes it so valuable. In the grand quest to understand cosmic architecture, astronomers need more than just the record-breaking giants. They need to study the vast, quiet majority. The Cancer supercluster represents that majority, a typical metropolitan area in the cosmic web, and by analyzing populations of structures just like it, scientists perform a kind of universal census that reveals the deepest parameters of reality itself. This process relies on statistics. Imagine you are an alien ecologist trying to understand a forest you have never visited. You cannot see every tree, but if you can study enough representative patches, some dense with old growth, some sparse with saplings, some with a mix, you can begin to deduce the rules of the entire ecosystem. The forest's overall health, its age, and the nutrients in its soil all leave an imprint on the distribution of its trees. Cosmology works in much the same way. By surveying large volumes of space and cataloging thousands of superclusters like Cancer, astronomers measure their statistical properties, how many there are of a given size, how far apart they typically are, and how their galaxies are clustered together. These numbers are not random. They are the direct outcome of the universe's recipe, the specific mix of dark matter, dark energy, and ordinary matter that has been sculpting everything since the Big Bang. One of the most critical numbers derived from this cosmic census is omega matter. This is the symbol for the total density of matter in the universe, a single figure that tells us the ultimate fate of all structure. If omega matter is high, the universe is dense with mass, and gravity will eventually halt and reverse the expansion, leading to a catastrophic Big Crunch. If it is too low, the universe will expand forever into a cold, dark thinness. Our observations point to a precise middle value, one where the expansion continues forever, but structure still had enough time to form into the great walls and voids we see. How do we know this number? By counting superclusters, the statistical clustering of galaxies, as seen in populations that include the Cancer supercluster, acts as a cosmic scale. The strength of this clustering, how strongly galaxies clump together into groups, clusters, and superclusters, is exquisitely sensitive to the amount of matter in the universe. More matter means stronger gravity, which pulls galaxies into tighter, more pronounced clusters. By measuring the exact degree of clumpiness in our maps and comparing it to predictions from millions of computer simulations run with different values of omega matter, astronomers can pinpoint the true value with remarkable precision. So, while the Cancer supercluster may not make headlines for its size or its emptiness, it plays a starring role in a far grander story. It is one data point among thousands in the ultimate statistical analysis, helping to weigh the entire cosmos and define the balance of forces that allowed galaxies, stars, and planets to ever exist at all. This chain of galaxies extends the Great Northern Wall like a celestial arm reaching deeper into the void. Known as the Pegasus-Pisces chain, it is a filamentary extension of the immense Perseus-Pisces supercluster, a tendril of matter that shows us the cosmic web's backbone in stunning detail. When astronomers plot the precise three-dimensional positions of thousands of galaxies in this region, a pattern emerges with breathtaking clarity. The galaxies do not fill the space like a random scatter of stars. Instead, they line up. Brilliant clusters and quieter groups of galaxies arrange themselves in a distinct, elongated chain, like beads strung on an invisible thread that stretches for hundreds of millions of light years. This alignment is not an illusion or a trick of perspective. It is a direct, visual confirmation of the filamentary structure predicted by our leading theory of cosmic evolution, known as gravitational instability. The theory begins with a nearly smooth, uniform universe after the Big Bang, a cosmos filled with a subtle sea of quantum ripples in density. Gravity is the artist that works on this canvas. Over billions of years, it acts as an amplifier. Regions that began with just a tiny bit more matter than their surroundings exerted a slightly stronger gravitational pull. This pull attracted more gas and dark matter from the neighboring areas, making the dense regions even denser and the less dense regions emptier. It is a snowball effect on a cosmic scale. But gravity does not pull matter into perfect spheres everywhere. Think of stirring a cup of coffee with a sprinkle of cinnamon on top. The cinnamon does not gather into a single ball in the center. Instead, it gets drawn into swirling lines and filaments that trace the currents in the liquid. In the early universe, the dark matter formed an invisible, web-like scaffold through this same process, and ordinary matter, the gas that would become galaxies, flowed along its lines. The Pegasus-Pisces chain is a fossil of that flow. It is a place where the gas pooled and cooled along one of these primordial dark matter highways, eventually collapsing into the brilliant galaxies we see today, all still tracing the original path. This chain provides some of the cleanest evidence for the theory because we can see the hierarchy of structure within it. At the intersections of this filament with others, we find the densest knots, the rich galaxy clusters. Along the quieter stretches, we find smaller groups and isolated spiral galaxies. It is a complete cross-section of cosmic ecology, all organized by the initial, gentle tug of gravity on a faint ripple from the dawn of time. Seeing this chain, so clearly mapped, is like finding the blueprint for a city, and then flying over to see the streets and buildings constructed exactly to plan. It tells us that the largest patterns in the universe were not random, but were written into the fabric of reality from the very first moments, and patiently drawn out into the light by the relentless, creative force of gravity. Our final stop in this local tour brings us to the winding constellation of the river, Eridanus. Here, a modest but pivotal gathering known as the Eridanus Group anchors an extensive, sprawling filament network that weaves through our entire cosmic neighborhood. This is not a single, isolated cluster, but the central knot in a web of faint, connecting threads that link many of the structures we have already explored. The Eridanus Group itself is a collection of a few dozen galaxies, a quiet suburban community compared to the massive urban centers of the Virgo cluster. Yet its importance lies not in its individual brilliance, but in its connections. This group is the gravitational heart of the Fornax-Eridanus cloud, that faint, elongated bridge of galaxies we discussed earlier. From this central point, faint tendrils of galaxies and intergalactic gas stretch outward, reaching toward the Fornax cluster in one direction and fading into the greater Pisces-Cetus supercluster complex in others. It acts as a cosmic roundabout, a junction where several local filaments meet and exchange material. This intricate network demonstrates a profound truth we are only now fully appreciating. For decades, our maps of the universe have been drawn with bold lines and clear labels, defining distinct superclusters as if they were separate continents on a cosmic globe. The Eridanus network shows us that this is often an oversimplification. The cosmic web is not a collection of isolated structures. It is a single, continuous, and breathtakingly complex network. The boundaries we draw are frequently arbitrary, based more on the limits of our surveys and our human need for categorization than on any true discontinuity in the distribution of matter. Where does the Eridanus filament end and the Pisces-Cetus complex begin? The transition is gradual, a seamless blending of one structure into another. Galaxies flow along these filaments like water in a branching river delta, their paths determined by the gentle slope of the gravitational landscape, not by the borders on our maps. This continuous network challenges the very idea of a cosmic address. We are not merely in Laniakea or on the edge of the local void. We are embedded within a boundless, three-dimensional tapestry where every filament is connected, every wall is part of a larger sheet, and every void is a shared chamber between multiple structures. The Eridanus Group, in its quiet way, embodies this fundamental interconnectedness. It reminds us that the universe's greatest mystery may not be the individual giants we have catalogued, but the invisible, seamless whole they form together, a single, flowing architecture of gravity, light, and dark, woven from the first moment to the last. This grand cosmic architecture presents a paradox of scale. Our leading theory of the universe, called the Lambda CDM model, is a masterpiece of modern cosmology. It tells a compelling story that begins with the Big Bang and a period of hyper-expansion called inflation. During inflation, the tiniest quantum ripples in the fabric of space-time were stretched to enormous sizes. These ripples became the seeds, the blueprint, for all future structure. After inflation, the universe was filled with a nearly smooth, hot soup of particles and two mysterious components: cold dark matter, which feels gravity but not light, and dark energy, which drives the accelerating expansion we see today. Gravity is the sculptor in this model. Over billions of years, it gently amplified those initial ripples. Dark matter, being cold and slow-moving, clumped first, forming an invisible web of filaments and halos. Ordinary matter, the gas that makes stars and galaxies, then flowed into these dark matter wells, lighting them up. This process, driven by simple, well-understood gravity, should produce a cosmic web. And it does. Our supercomputer simulations, based precisely on Lambda CDM, generate stunning virtual universes that look remarkably like the one we see, complete with filaments, clusters, and voids. But there is a catch. The largest structures in our simulations, while beautiful, do not quite match the extreme giants we find in reality. The model predicts a certain statistical range for the sizes of walls and voids. It tells us how big the biggest lump in the cosmic batter should reasonably be, and how empty the deepest hollow can become if everything started from those tiny, random quantum seeds. The Sloan Great Wall, the Hercules Corona Borealis Great Wall Candidate, and the Boots Void are not just big, they are outliers. They sit at the very edge, or perhaps even beyond, the predicted distribution. They are cosmic statistical anomalies, like rolling a dice a billion times and getting a sequence of 100 sixes in a row. The universe, it seems, has produced structures that are too big to easily exist within the standard story, and voids that are too empty to have formed by gravity alone. This is the core mystery the Great Wall's force upon us. Is our universe simply a rare statistical fluke, a one in a trillion roll of the cosmic dice that just happened to produce a few breathtaking giants? Or is our model missing a crucial ingredient, a physical process that provided an extra push, an additional organizing principle, in the universe's earliest moments that helped build these colossal features? Some scientists are exploring fascinating alternatives. Could immense primordial magnetic fields, woven into the fabric of space in its first second, have provided a scaffold that guided matter into larger clumps than gravity alone could manage? Might there have been dramatic phase transitions in the early universe, akin to water freezing into ice, that created shock waves and bubbles, imprinting preferred scales on the distribution of matter? Others look further afield, to exotic physics beyond our current standard model. Could a different type of dark matter, one that interacts with itself or with light in a subtle way, have changed how structures formed? What if the force of gravity itself behaved slightly differently on these immense intergalactic scales? Each of these ideas is a potential key to the puzzle, a way to nudge the simulations so that their largest structures grow to match the titans we observe. They represent the thrilling frontier of cosmology, where the universe's greatest monuments are challenging us to rewrite, or at least refine, the story of our origins. The Great Walls are not just distant curiosities, they are cosmic interrogators, demanding we explain how they came to stand against the dark. These colossal walls and profound voids are not isolated wonders, but chapters in a single, unified mystery. They are the universe's own handwriting, scrawled across billions of light years, and we are only just learning to read it. From the immense pull of the great attractor to the silent push of the dipole repeller, from the filamentary threads of the Pegasus-Pisces chain to the spherical perfection of the Boots void, each structure tells us something vital. Together, they reveal a cosmos that is not smooth and featureless, but wildly textured, organized on a scale that humbles our imagination. This grand architecture is the ultimate challenge to our theories, a cosmic stress test for everything we think we know about dark matter, dark energy, and the forces that shaped reality from its first instant. The very existence of these giants whispers that our map, however detailed, is still incomplete. They are the outliers on the graph, the anomalies in the data, the features in the tapestry that our most elegant models struggle to explain. Do they point to a flaw in our understanding of gravity itself? Could they be fossils from an era before inflation, or signatures of physics we have not yet discovered? Each unanswered question is not a failure, but an invitation. It is the universe daring us to look deeper, to think bigger, and now we stand on the brink of a new era of cosmic cartography. The next generation of observatories, like the Vera C, Rubin Observatory, and the Euclid Space Telescope, are not merely upgrades, they are revolutions in perception. They will scan the sky with such depth and precision that they will not just map galaxies, they will trace the dark matter scaffolding between them. They will measure the shapes and distances of billions of galaxies, turning our current sketch of the cosmic web into a high-definition, three-dimensional atlas. This new map will either confirm our standard model by showing these great walls are rare statistical flukes in an otherwise predictable pattern, or it will reveal that they are part of a deeper, more profound order we have yet to comprehend. It may solve the mysteries of the Hercules Corona Borealis Great Wall and the KBC Void, or it may unveil structures so vast they make our current giants seem provincial. The journey to understand our place in the cosmos is accelerating. The greatest chapters of this story are not behind us, written in the light of ancient galaxies. They are ahead, waiting in the data streams of the next great telescope, in the curiosity of the next generation of explorers. Our universe has built its monuments. Now, it is our turn to decipher their meaning.